Good morning, everyone. I'm Luca Franceschelli. I'm supervised by Stefano and Marco, and my PhD thesis is about active control strategy for jet flows using an advanced flow diagnostic. But let me start with the question: why can't we have an airport in Madrid center, like in Madrid Atocha? Well, this is the footprint of the noise produced by a landing airplane on a city, and you can see that it is really disturbing the people. Like, this is a random guy walking in San Diego, clearly disturbed by the noise generated by the aircraft. Now, noise generation means health risk, which means regulations. Regulations which force the manufacturer to reduce the noise production in more than 80% since the beginning of commercial aviation in the 60s. But there's still a lot to do. So for 2050, we're expecting a 65% decrease more of the noise production by aircraft. And if we break down the different noise sources of in this case, a departing aircraft, we can see that most of it, kind of half of it, is due to the jet noise, which means an acoustic problem, meaning that this noise is generated mainly by the structures of the jet, which are joining with the environment. The fast air jet, which is exiting from the engines, which is mixing with the rest of the air and is creating the noise. Now, and my thesis goes into this direction to reduce the noise generated by the jets. This is a typical case scheme of control for any physical system that we are going to apply to fluid flows. So we have a physical system defined with a certain state X and a certain dynamic defined by X dot. We have actuators to act on that, which is B. We have control loads that depends on the sensing. And when we try to apply this kind of scheme to the control of fluid flows, we go into many issues. First of all, the nonlinearity of the system, because as we know, physical system fluid flows are governed by Navier-Stokes equation, which are highly nonlinear, which leads to a highly nonlinear system for us. Then there's also a very high dimensionality, which is what also Alicia was presenting before, which means that in order to describe completely the state of a fluid flows, we need a lot of points, which can be the grid points of CFD simulation or of PAV measurement. Not only that, we have also issues for the authority of actuators in our case, and in case of the very promising approaches based on machine learning for flow control, we are usually lacking of interpretability of the control actions, which doesn't allow us to extend such control actions to study the physics of the control. So my thesis is aiming to design and implement this kind of experimental framework to develop active jet flow control strategies and extract interpretable control solutions. So if we go into the details of this scheme, we started from the physical system, which means our experimental setup. So we started by our room in order to provide a real kind of free field environment. What we need to do was to avoid the reverberation inside the room. So we had to put all the necessary acoustic insulations. And from the point of view of the fluid, we had to avoid any kind of flow recirculation inside our chamber, which meant that we had to design and implement a new kind of secondary wall where we had like the extraction of the dissipation and extraction of the recirculation flow. Now, once this was done, we could characterize the facility, and the results were presented at the conference at the AIAA last year in Rome. Now that we have our beautiful jet flow facility, we can move on with the rest, which is actuators. So we want to act on the jet flow. How do we do it? As most of turbulent flows are characterized by some coherent structures, which are some kind of dominant pattern in the dynamic of the flow. And these are really important for the noise generation and the mixing control. This is a kind of visualization I tried to do with exciting this kind of main structures, where I was like actuating with some acoustic forcing, and I was looking with the camera what was happening in the flow. And what you can see is that we have these kind of most energetic structures in the jet flow, which are typically axisymmetric or helicoidal. So we know that we want to act mainly on these to control the jet flow. But how to do it? So we went through different kind of actuators. We decided to go for synthetic jets. Synthetic jets is basically a cavity, like this one on top right, which with a membrane at the bottom, which is changing the volume, which is oscillating and changing the volume. This change in volume is ejecting a trail of vortices, which is kind of producing a trail of vortices, which is providing some momentum into the flow. The nice thing about this is that these are zero net mass flow actuators, meaning that I'm not introducing any kind of mass flow inside of the jet. They're pretty easy and compact to be implemented. And so we kind of designed our own. We tested them. We have a loudspeaker at the bottom, which has a membrane which is oscillating and is providing an exit velocity. Once we have these, we could characterize it, meaning that we could define, depending on the frequency of actuation and the amplitude of the actuation, we could have a certain exit velocity. And once we have this, we could mount our setup. And in this, what are we doing now is that we put 6 of these acting radially at the exit of the jet, this is the exit of the jet nozzle. So we have the actuators, we have our physical system. Now, control law. As I said, there are very promising methodology nowadays based on machine learning, but what is lacking usually is interpretability of what is going on. So how can we get some interpretability of what we are really doing on the flow? We try to do some flow estimation, meaning that usually in experimental setups, what you have is like you have your flow, you can put some probes, get some velocity or pressure measurement, and you get a very nice time to solve the series of your information, but it's only point-wise. On the other hand, we have PIV, which allows us to have spatially resolved measurement, but typically it's impossible to have this time resolved. So what we want to do is like kind of try to exploit the time resolved probe measurement and reconstruct the full flow field also in between the different PIV measurement. This is what we call the enhanced time resolution of the PIV, of the non-time resolved PIV. So this is what I tried to do basically during my first year here, and it was not really successful, but it's something we are going to implement again, but with a different approach. Also because now we kind of came up with a question, because up to now we have always used PIV as a kind of diagnostic tool, meaning that we never thought about using that in the control loop itself. Why? Because what we want to do is that basically you would like to have the PIV directly sensing your flow, but since it's a flow that is evolving super fast, and I mean like the dynamics has to be at least in the order of 100 of hertz, it means that if you want to act that fast, you need to sense even faster. And having PIV system going that fast with such a time resolution is pretty complicated. So what was typically done was like in your flow field, that your probes, you could measure the velocity, as I said also before, and PIV was only for diagnostic. But what if we could provide this kind of information to the controller, like the full flow field, the topological information? It would increase a lot the observability of our system, and probably would allow to explore different control strategies. Now, in order to do this, there is a kind of change of framework in the paradigm in the cameras, because up to now cameras were always like frame-based cameras, meaning that these cameras were like based on an internal clock. They were acquiring at a certain fixed time frequency, and you were downloading the image. What recently was developed and commercialized are these neuromorphic cameras, which are inspired to the human eye. These kind of cameras are completely different in the sense that now the sensor is composed of asynchronous and independent pixels, meaning that a pixel activates only once it sees a contrast change. What this provides? It provides a series of advantages that are born for mainly drones or autonomous vehicles where you need to have very low power consumption, very low data, and a very slim data stream. But we thought, why don't we try to apply this to PIV measurement? So the main question was, we know we're probably losing some quality in the measurement, but is it going to be good enough to catch the flow dynamics and apply that for flow control? So what we basically did was we tried to compare the two measurements with like very expensive high-speed cameras like this one in 0.3 in the order of 200,000 euro, and we compared it with this very small and cheap camera, which are like 200 times cheaper. And long story short, it works. It worked very well, meaning that we could get the same dynamic of the main flow structures as if we were observing with very expensive cameras. Once we had this kind of result, we said, okay, now let's try to implement this in our control loop directly. And this is what we are doing actually in the last month together with people from Politecnico di Torino and Enrico. And this is like the scheme that we just implemented in our facility, where we have the event-based camera, which is sensing what is exiting after the jet with our actuation with the six actuators. Then this is providing a reward for the control strategy, which is based in Bayesian optimization or reinforcement learning. We are exploring both of them, and this is the actual the experiment which is running now, which is also interesting because it allowed us also to work with very cheap laser sources. And this is the ongoing work of the moment, but actually it's running just now, and long story short, it's working, but this is stuff for next year probably with the full results. The timeline of my PhD, basically now we are finally working at the third year with real control of the jet flow. We are doing also different approaches, trying to study the dynamic of the jet and the control jet. And on September, I'm going to that for research day, trying to expand even more the experiment on jet flows. These are a bit of the outcomes. There is the journal paper about the comparison with event-based cameras and few conference contributions. Thank you.